Hey, welcome back. So we discussed about linear regression in our last session, and the point was if there are two variables and if they are linearly related to each other, then we can come up with some kind of a linear equation which can be represented as the form of y equal to mx plus b. So we will have something like the slope and the intercept. Of course, then this was represented as beta 1 and this was beta naught. Okay. So the point was to understand if this beta 1 is really significant or not. So we stopped at a point wherein we tried to understand that we should go and apply some kind of a statistic test to validate this beta is really making sense or not. So we'll be covering that in today's section. So just the takeaway from the previous session was if there is a relationship, then we will have to represent that relationship in some kind of a linear equation. Just just keep that in mind. Okay. So now what we'll be doing is we will be looking at the other parts. Say for example, we have covered all this. Okay, we also covered this point wherein what are the assumptions that we should be looking at before we go and apply the linear regression model. So the points that we discussed was this. The first point was to note that there is indeed a linear relationship between the target variable and the independent variable. So in this case, the target variable can be your weight and the independent variable can be your height. Okay, and the second assumption was the errors that the model is making should not have any kind of patterns. So if I when I say patterns, it should not look like this kind of a thing. So when you have this kind of a thing where you have equal lift and drops, it means that it is most likely a time series problem, and a linear regression cannot handle such data sets. So that's a different thing. Maybe we can discuss time series like ARIMA and ARIMAX at a later point. But for now, just keep in mind that the error terms should not be. I mean, it should be pretty much random, and it should not have any uh, some kind of a pattern to it. And the third assumption was that the error should be homoscedastic. It means that the it should be at equal distance from the center. Okay, and if it is heteroscedastic, you would have uh, something like this. That would happen generally if you have an outliers. Okay, if it is heteroscedastic, probably the linear model will not work properly, and you'll have to treat the data set in before we go and apply linear model. And the last assumption was the error term should be uniformly distributed, and the quartile plot should look like the last thing, like it should look like this. Okay, these are the things that we discussed in our last session. Okay, now there might be a couple of cases where the relationship is not linear, but we are still trying to go and apply the linear model. So what should we do when the data is not linear? So there are a couple of things that we can go and try out. Say if you can go and we can always go and apply some kind of a square root or log and see if by applying log if it is converted to a linear space or not, or by converting the lower dimensions to higher dimensions if the data become normal or not, linear or not. Say for example, if you have a two-dimensional space, there might be a case where when we convert a two-dimensional space to a three-dimensional space, the non-linear thing which is present here can become a linear thing here. Maybe you can have hyperplane, something like this. It's some kind of an assumption that we can have that when we convert to a lower dimension space to a high dimension space, we can at least go towards linear relationship. This might not work in all the cases, but this is also there. Okay, let's go to today's topic, wherein we are going to discuss about once we have the model, what should we be checking at? Once we have the model and we know what are the slope parameters and the intercepts, we should be checking for if the slope is really making sense or not. So statistically, we have to go and check whether the slope is really the value which is shown by the model or it is something different. So how to check that is by applying some kind of a hypothesis. Okay, we'll discuss about hypothesis in some few minutes. But given a case that there is a relationship between our x and y variables, if there is a relationship, then there should be some slope. If there is no relationship, then the slope should be zero. Yeah, this is what we're going to cover in today's session. And we will also run a couple of codes to check to prove that it really has some significance, like the independent variable is having some significance to the dependent variable. That might not happen, it might depend, it might vary from case to case, but just keep that in mind. Okay, so let us say that we achieved a model and we are going to calculate the y hats by this formula, beta 1 x plus beta naught. So you have this model, and using this model, we can go and calculate our y hats, and we can go and calculate the SSEs, sum of squared errors. Okay, that's a different thing. So we will discuss if this B1 is really making sense or not. So we should run some statistical tests to prove that really there is a relationship. So what should be our null hypothesis is, null hypothesis will become like there is no relationship. The slope will be zero. And if there is no relationship, I can predict y hat without having my x values. That is what my null hypothesis says. My model says it is already y hat is equal to beta 1 plus beta 1 x plus beta naught. My model says that. Now I want to validate if my beta 1 is really correct or not. So for that, my null hypothesis says just the alternate of what the model says. My model says there is a beta 1, but my hypothesis should be like there is no slope. When I say m, it is like beta 1. The beta 1 should be equal to 0. This is what this will be our null hypothesis. And alternate hypothesis, h, it can be represented as h1 or ha. In both the cases, it is like m is not equal to 0. It can be any number other than 0. So if it is any number other than 0, it means that there is some relationship between y and x. And you will require x to go and predict y. Of course, you might have some intercept, but x is required. Without having x, you cannot calculate the y. That is what the alternate hypothesis is. For this, what we would be doing is we would be going and calculating what is our t statistic, and based on the t statistic, we'll find the p-value. Okay, this is the probability value, and we'll check if the probability value is less than 0.05. Then we will reject the null hypothesis and accept the alternate hypothesis. If the value is greater than 0.05, it means that null hypothesis cannot be rejected. It has to be accepted and alternate should be rejected. So when you notice that the p-value is greater than 0.05, the model is not correct. Though it is saying y is equal to mx plus b is there, but the model is not correct because the means are not saying there is no statistical evidence to prove that the model is correct. Okay, so we should be revolving around these concepts of calculating the t-value, interpreting it the p-value from t statistic, and then checking the significance. So when I say we are checking for significance, we are just checking if the value is less than 0.05 or not. Okay, so we will just go and have a Python session wherein I'll try to tell you how we are doing this. Let me clear my drawings. So let's go to Python notebook. So you can have this, you can get the link to this particular code on this GitHub. You can always go through the notes that I have written already. So what we'll try to do is like we'll try to take a small data set. In this case, it is like a small students data set that we have downloaded from this Berlin.t site. And this is how the data set looks like. We have a lot of records and a lot of columns. The shape is about 839 records. Sorry, 8,239 records with 16 columns. But we will not deal with the whole data set. For now, our instance, our lookout is only by considering two variables. Now I want to look at my height and weight. For a given height, I want to check if I can predict the weight or not. So how do I do that? So for subsetting, I will take two columns. That is how I subset. I use a double square bracket. I take the necessary columns into my data frame and assign it to a new variable. Now in the new variable, you have only two columns, height and weight. What is the next thing? We will go and check if there is a linear relationship or not. We will not run the whole test. For now, it is a simple data set, so I can use matplotlib and check if there is any linearity in the data. So how to do that is by taking some random samples. So I took some 21 samples from the data. Here you have data, and from this data I'm taking samples of 21 records and I'm storing it in data sample. Okay, this is how my data sample looks like. They are completely random and the shape is like 21 records and two columns. So I'll just go and plot my height and weight. My height is on my x-axis and the weight is on my y-axis. As you can notice that there is some kind of a relationship. Okay, I can come up with some approximation saying that this could be my linear model. And given a case when I get a height of a person, given a case that when I get a height of a person, I can go and calculate what is the weight. So for example, if the height of the person is something around 178, then the weight could be somewhere around 78. That is what I would be doing. Okay, so let us go and apply linear model. So what is the thing that we require for linear model? We require beta 1, which is nothing but a slope. So we'll calculate the slope here. So for calculating the slope, we have some simple formula. We will be checking the covariance of height and weight. Okay, so how does height correlate to weight? We will measure the covariance. Now we see that the covariance is 114.5. This makes no sense to us. Like we don't have to go and check the covariance of height of with itself. Similarly, we don't have to check the covariance of weight with itself. That makes no sense to us. What we should be looking at is the covariance of height with weight, and there is some value 114. So you remember from our last discussion, like when the covariance is positive, it means that there is some relationship and it is a positive relationship. As x increases, y also increases. That is where we have this covariance as a positive number. Okay, and then what we'll be doing is we'll try to calculate the slope. Now in this case, the slope is nothing but beta 1. How I calculate is I'll simply take the covariance values of height and weight and divide it by the variance of my sample, of the height sample. So when I do that, I'll get my beta 1. So the beta 1 is 0.8. You don't have to worry about the formulas. It's only for our understanding purpose that we are going to this deeper level. When you go to applying the actual models, it will be a simple library wherein we can just simply import it, apply it, and the library will tell you what is the uh, uh, parameters for the linear regression model that we have come up with. Okay, so that is how we can find the beta value by applying this formula, and this is how you got the beta value. Now if you notice, we have a equation y is equal to mx plus b. You know the y and m values. We simply have to go and calculate the beta c value. It should be mx plus c. Okay, so how do you calculate c value? Simply by saying y minus mx. So in this case, my y is weight mean and my m is nothing but my beta, and my x is nothing but my height mean. So when I calculate that, I get an the intercept value c as minus 65.24. So what should be our equation? Our equation would be, or linear model would be, uh, it would be like lm underscore beta into your height. So in this case, data underscore sample says height plus lm alpha. This is my model. I have mx plus c model. Now, if I have to go and calculate my y hats, I can simply calculate it. So what is my y hat? Y hat is nothing but the same thing. I'll pass my x values to the linear equation. I'll get my y hat. So in this case, instead of x, I have height. And when I go and calculate, these are the values. These are the predicted values. These are the predicted values, and you have the sum of squared errors as 120. Okay, and as compared to the ground truths. Now, what is my ground truth? Say, for example, for the first one, the ground truth is 60.4, and we are getting 62.4, approximately somewhere close to the real value. And this for the second one, it is 74.2. It is also 74.5, somewhat near. Okay, so we'll go and calculate what is our error. In this case, we are taking the square root of squared errors and dividing it by n minus 2. So we have a standard square error as 2.5. And then we'll calculate the t value out of it. So when we calculate the t value, it is something like this. We'll calculate the slope divided by SC into square root of this sample. Okay. So when I do that, I'll get the t value. So the t value is around 17.05. Once I have the t value, I can go and calculate what is my p value. So p value would be using the stats library dot t dot cdf and pass our t value to it with the degrees of freedom. So as we have 21 samples, the degrees of freedom will become 19, and at 19 with this t statistic, we will be getting the p value. So 1 minute. So the p value is somewhere around 5.6174 to the power of minus 13, 10 to the power of minus 13. So this value is very small as compared to 0.05. So it means that we can reject the null hypothesis and accept the alternate hypothesis. So what we are doing here is, in the hypothesis testing, we are trying to find out that let us say that this is a uniform normal distribution. You have error here as well as here. So here it is 0.025 and here it is 0.025. So put together, it will become 0.05. So when you're doing a t-statistic test, you're trying to find evidence if the mean is present in this region or not, this region or this region. If it is not present, like if you do not find any probability of finding the mean in this region, it means that the probability of finding the mean in this region will be very high. So we cannot compare, we cannot look for the mean. It can be present anywhere, but we're just trying to check if it is present in the error region or not. If it is not present, how you can tell it is not present is by checking the p-value. If the p-value, if the p-value is less than 0.05, it means that the means 95% of the times they're always at the center and not at the ends. When they're not at the ends, it means that maybe your height mean is somewhere here and your weight mean is somewhere here. They'll be very nearby to each other. So when they're very near to each other, it means that they are correlate with each other. That is what the alternate hypothesis and null hypothesis testing is. So in this case, because you find that the p-value is less than 0.05, we will reject the null hypothesis, which says m is equal to 0. Correct? We started off by assuming that my null hypothesis is m equal to 0, and my alternate hypothesis m is not equal to 0. This is my null hypothesis and this is my alternate hypothesis. So you could not find evidence saying that the slope is present in error region of 0.05. That is why you try to reject the null hypothesis and accept the alternate hypothesis. And when you're accepting the alternate hypothesis, you're trying to tell that slope is not 0, and definitely x variable can be used to go and predict y. In this case, I can use height to predict weight. That is what the linear regression revolves around. Okay. So similarly, you can also go and apply test for the whole complete model, which we call as F statistic. Just like we have p value, we will also have like F value. We will cover it when we are dealing with the programming code. and then we'll try to find out if the f value is less than 0.05, then the model is also good. So we'll say that the independent variable is good to predict the y variable, and the model is also good to predict the y variable. Okay, that is all about t-testing. So let's go back to the presentation again. Okay, and then what happens is, like, once you are done with the alternate hypothesis testing, we will go and check what all other things that we need to look at. Say, for example, you have couple of cases where you trained a model, and you might notice that the r square is somewhere around 97. Okay, just by looking at r square, we cannot tell that the model is good. Okay, uh, just not, the numbers can deviate. It can, we can interpret the numbers in many different ways. Say, for example, if your p value is greater than 0.05 and your r square is 97, it says that the variance is explainable, like the model is trying to can explain all the variance up to 97%, but because your p value is not good enough, actually it is not dependent on x, but your model is dependent on x. So the way you interpret might be confusing, so you will have to be very careful when you're using any model. For that matter, it need not be just linear regression. You can use any model out in the market, but we need to be cautious about what conclusions we are drawing from those numbers. Okay, and the linear regression, as in this case, like we had height here and we had weight on the y-axis. So if I go and predict the weight of a person, given that their height is like 285 centimeters, okay, this technically is not possible. Like, when you have a wherein you have 285 centimeters person, but your model will still go and predict it. How it will predict? It will say 0.8 into 285 minus 65. This is my weight of the person, but technically this data might be not a valid data, so we have to be careful that we need to have some upper limits and lower limits for our predictions. So if you know that the maximum limit of the model should be, like, say 120 kgs, then you have to go and apply some rules on top of it, saying that, if it is crossing beyond 120, make it 120 or something like that. Or maybe even in the case of samples, you can say that, I'm good to predict up to, say, a height of 200 centimeters. So beyond 200 centimeters, if you're getting anything, like, you can return some message saying that, this looks like not a valid data or something like that. So that is all about linear regression. Maybe in our next session we'll be covering all about more complicated features. Now we covered only a simple variable, like we saw y is equal to, like we saw y hat is equal to beta 1 x plus beta naught. So what if there are more features to it? What if there is x1, x2, x3? So our y hat should become like beta 1 x1 plus beta 2 x2 plus beta 3 x3 and x naught. Sorry, it should be beta naught. Should be beta naught. So you're representing a multiple linear regression, and you're trying to make a model out of this. Okay, it is just like a three-dimensional space wherein you have x1, x2, and x3. So like this, you can have n-dimensional space, and we will try to cover this in when we are dealing with the Python code. We'll try to cover this part also. Okay, I think we should be good for today's session. Let's touch base on the next session. Thank you.